This is a video about simple harmonic motion. Let's look specifically at the simple harmonic motion of a block connected to a spring. The force necessary to apply a force to the block to move it a certain distance would be called the applied force. Now, the force that pulls back in the opposite direction would be the elastic force, and it would be in the opposite direction because it's pulled in the opposite direction. We put a negative sign in front of it. So that's why there's a negative sign in front of what we call Hooke's law. Now, if we look at the variables for Hooke's law, F stands for the restoring force. Its units are in newtons. K stands for the spring's constant. Its units are in newtons per meter. The spring constant tells us how much force is necessary to pull a spring a certain distance. So the stiffer the spring, the higher the spring constant. X is the displacement that the spring experiences when it's pulled, and its units are in meters. The maximum displacement of a spring is called its amplitude. Now this equation tells us the period of a spring. The period is the amount of time it takes a spring to go an entire cycle. M stands for the mass, and it's in kilograms. This next equation relates the period of the spring to the frequency. The frequency is the number of cycles per second. If we graph what we call an ideal spring, so this is a graph of an ideal spring, we find some very important features of the graph. The first feature that we'll notice is the fact that the slope is equal to the spring constant. The next feature is the fact that the area represents the work done in extending the spring. In this graph, or in this slide, we'll look at where the velocity, acceleration, force, kinetic energy, and potential energy are at their maximums and minimums. Now, let's observe the block as it goes back and forth. The first question is, where is the velocity at its maximum? Well, it's at its maximum when it's at the middle or equilibrium position. It's at the minimums at the ends. The acceleration is a maximum at the ends and a minimum in the middle. And if we look at the forces correspond to the accelerations. Because of Newton's second law, where F is equal to ma, because the accelerations are maximums at the ends, then the forces must be maximums. Because the acceleration's a minimum in the middle, then the force will be a minimum at the middle. The kinetic energy is related to the velocity. So the maximum kinetic energy will be where the velocity is at a maximum in the middle. And the minimum kinetic energy will be where the velocities are at a minimum, which are at the ends. The potential energy is a maximum at the ends because that's where the amplitude or the displacement is at its greatest. It's related to the equation 1/2 kx squared. And so x is a maximum, or is at its amplitude at the ends. And it's at a minimum in the middle. This is an animation of a pendulum. A pendulum behaves with simple harmonic motion as long as the angle is really, really small. So one of the things that we need to make sure is that this angle theta is relatively small. The period equation tells us that the period of a pendulum is equal to 2 pi times the square root of L over G, where L represents the length of the pendulum, and G represents the acceleration due to gravity, and as we know, on Earth, that's 9.8 meters per second squared. Now notice that the period only depends on the length, as long as obviously we're on the Earth. It doesn't depend upon the mass. It doesn't depend upon how far we pull it back or anything else but the length. The frequency equation, or the period equation as it relates to the frequency, is the same as that of any type of simple harmonic motion, where the period and frequency are inverses. Here's a simple harmonic motion problem. It says a block of mass M is resting on a horizontal frictionless table and is attached as shown above to a relaxed spring of spring constant K. A second block of mass 2M, initially V initial, collides with and sticks to the first block. We need to develop expressions for the following quantities in terms of M, K, and V initial. Now, before we get started, one of the things we need to remember is that simple harmonic motion problems, because it is a type of mechanics problem, can still be solved using our general physics or our universal physics rules. Remember, one of our strategies includes a force toolkit, so we could still use a force toolkit in solving these problems. We could still use energy conservation, or in our case, in our class, we call that the energy model, and we can still use conservation of momentum. For question 1A, we will use the conservation of momentum. So we need to make some conservation statement. For example, we need to say momentum is conserved. And we need to make a momentum equation. So something like the P initial is equal to P final. Now, the problem tells us that this is a completely inelastic equation. So we know that the masses are going to combine afterwards and stick together. In general, we know that the momentum is equal to M times V. So if we look at the initial momentum, the mass is just the 2M mass because the 1M mass isn't moving yet, so we're not going to include its momentum. So the 2M mass is the only one that's moving, and it's got a velocity of V initial. We don't need to include the other mass because it has no velocity, therefore it has no momentum. They tell us it's an inelastic collision, so since it's an inelastic collision, the 2M mass combines with the M mass, and they have the same velocity V. So if we solve this equation for V, we essentially get 2M V initial over 3M. The M's cancel, and we get 2/3 V initial. For question B, we'll use the energy model. So we'll look specifically at the energies at the beginning, which include kinetic energy, or which can potentially include kinetic energy, gravitational potential energy, and elastic energy. And because all of the energy right after they collide is kinetic energy, we know that we've got kinetic energy at the beginning. And at the end, we've got all elastic energy. Oh, you know what? We should also include our system. Our system should include the spring and the masses. So in this case, our energy conservation or our energy statement should be energy is conserved. And we should also write an energy equation. In this case, that all the kinetic energy at the beginning equals the potential or the elastic potential energy at the end. So generally speaking, that would be 1/2 mv squared is equal to 1/2 k, which is a spring constant, times the extension squared. Let's plug our values in. So on this side we would have 1/2. So the m would be 3m because, again, it was an inelastic collision, so they stuck together and they have a mass of 3m. Then the velocity would be 2/3 v initial, and that would equal 1/2 kx squared. And in solving this problem, we would get x is equal to the square root of 4m v initial squared over 3k. Question C says to find the period t of the simple harmonic motion. So we know that the equation for that is 2 pi times the square root of m over k. And because we know that the masses are actually 3m, it would be 2 pi 3m over k. So there we go. For part A, we use momentum conservation to find the speed of the blocks immediately after the impact. For question B, to find the maximum distance the spring is compressed, we use the energy model. And then for C, we simply plugged into this equation.